All right, let's dive into something pretty wild today. What if I told you that a simple geometry mistake, one that we can all understand, might have been hiding in plain sight in the world of physics for over 100 years? It's a bold claim, so let's get right into it. So let's start by putting you in the hot seat. Imagine you've got a laser and your target is just screaming past you at 10% of the speed of light. I mean, that is ridiculously fast. How in the world do you actually hit it? That's the puzzle we're going to unpack together. Now, a shot like that, it sounds basically impossible, right? But it's actually a classic physics challenge. And it's one of those problems that really forces you to think carefully about how time, distance, and motion all work together. At its core, this whole thing is a problem of what's called deflection shooting. Now, that sounds super technical, but I promise it's an idea you already get. Think about it. If you're throwing a football to a friend who's running, you don't throw it right at them, you throw it to where they're going to be. You have to lead the target. It's the exact same idea. Okay, so let's get down to the specifics. The thought experiment we're looking at today gives us a really clear scenario to play with. So let's just, lay out all the facts of the case. The setup here is actually beautiful in its simplicity. To keep the math from getting crazy, we're just going to say the speed of light is 1 unit per second. The train is moving at a tenth of that speed, and you, the shooter, are standing perfectly still at position 0, while the target is on the ceiling of the train 10 units straight up.
So just to recap the whole scene, we've got a stationary shooter, a super fast train, and a target on the ceiling. And the goal is simple. Fire your laser and score a direct hit.
Now, the source material breaks this problem down into 3 different strategies, almost like 3 levels of thinking. We're going to treat it like an investigation, and we'll look at each attempt to see where it goes right and, more importantly, where it goes wrong. First up, we've got strategy number 1. This is the instinctive approach, the one pretty much everyone would try first. You see the target, you aim at the target, simple as that, right? Well, as anyone who's ever played a first-person shooter knows, this is the classic rookie mistake. And of course, it's a complete whiff. You're aiming at where the target was a split second ago. But light, even though it's fast, still takes time to travel. And in that tiny amount of time, the train is long gone. So, strategy number 1, total bust. Okay, so on to strategy number 2, the much smarter approach. This is that leading the target idea we talked about. This time, we're not going to be dumb. We're not aiming where the target is, we're going to predict where it's going to be. And the logic here seems pretty solid. The target's 10 units high. Our laser travels at 1 unit per second, so it should take 10 seconds to get there, right? Okay, in those 10 seconds, the train moves forward by 1 unit. So all you have to do is aim at that future spot. 1 unit over, 10 units up. I mean, this feels right, doesn't it? It's logical, it accounts for the train's speed, the light's travel time. This has to be the answer. But is there maybe a little flaw hiding in that seemingly perfect plan? And here it is. This is the hidden catch. We calculated our 10-second travel time based on the light going straight up. But we're not aiming straight up anymore. We're aiming at an angle, creating a diagonal path. And if you remember anything from geometry class, it's that the diagonal side of a triangle is always longer. The actual distance the light has to travel isn't 10 units. It's more like 10.05. So because the light has to travel that slightly longer path, it takes just a little bit longer to get there. We're talking about an extra 5/100th of a second. But in that tiny, tiny slice of time, the speeding train has moved just a little bit farther. And the result? A near miss. The laser hits the ceiling right behind the target. So close, but still a complete failure. This brings us to our final strategy. Level 3. If a simple prediction isn't good enough, we need to find the true meeting point. We can't just guess where it will be. We have to solve for the exact single point in space and time where the laser and the target are guaranteed to meet. So how do we do that? Well, we set up a little equation. Let's call the actual time it takes to hit the target A. So in that amount of time, A, the light travels a distance of A, and in that same amount of time, the train moves a distance of 0.1 times A. And what do you know? The light's path, the train's path, and the height, they form a perfect right-angled triangle, which means we can use the good old Pythagorean theorem to solve for A. And when we solve that little equation, we finally get our real answer. The true time of impact isn't 10 seconds. It's not even 10.05. It's this very specific, very precise number, about 10.050378 seconds. That is the exact moment everything lines up. And what that means is the shooter has to aim just a little bit further ahead than they thought. But by using this final, complete calculation, they score a perfect, direct hit. The puzzle is officially solved. Okay, so that was a fun little geometry puzzle. But here's where this whole thing takes a massive turn. The source material makes this huge leap, and it proposes a really wild idea that this exact error we just saw, stopping at that stage 2 thinking, is a fundamental mistake that's been sitting in physics diagrams for 100 years. And this is a direct quote from the source. The argument being made is that some of the most famous, most important experiments in history, like the one that helped pave the way for Einstein's theory of relativity, are often drawn and explained using the flawed logic from our strategy number 2. You know, the one that we just proved leads to a miss. So what's the big deal? Well, here's the alleged consequence. According to the source, when you use that incomplete stage 2 calculation, you create a paradox, a situation where the math just doesn't add up. And to solve that paradox, you need to come up with these really complex, mind-bending explanations like time itself slowing down. But, the argument goes, if you just use the correct stage 3 calculation from the start, there is no paradox. It's just simple geometry. And to back up this claim, the source presented this entire argument to an AI model. Now, at first, the AI sided with the standard conventional view. But after being walked through the 3 stages, just like we were, it dramatically shifted its analysis. In the end, it gave an 85% validation to the source's geometric argument, compared to 0% for the standard interpretation. So what's the big takeaway here? Well, the source material presents this as more than just a calculation error. They frame it as a fundamental fork in the road for physics. Is the universe really governed by these complex, strange rules of spacetime, or is it all based on the straightforward geometry of hitting a moving target? And that really leaves us with a fascinating and pretty provocative question to think about. Is it possible that a simple oversight in a geometry problem, the tiny difference between a near miss and a direct hit, could have sent physics down a 100-year path of paradoxes and curved spacetime? Or is this just a really clever puzzle? The source leaves that up to us to decide.